Okay.
Let's go. So last time we started talking about a new topic that we call partial fractions. I think I'll just restart it again to repeat some of the things that are from the last time. Since it's kind of stopped in the middle. So just remember the process of breaking up a larger fraction into smaller reduced fractions. This can make it this can be useful for integrating, among other things. But we actually had a process to this, so let's actually go back to that process. One is, if your fraction is the wrong word for a rational function. Fraction is not proper, you must reduce it. You can do this using algebraic manipulation. Or something like long division. Give some examples of that. This means, proper means the highest power on the top should be smaller than the highest power on the bottom. If the highest power on top is greater than or equal to the highest power on the bottom, you have to reduce it before partial fractions can be done. And sometimes after reducing it, partial fractions might not even be necessary because you'll be able to deal with the thing as manipulated. The second thing you'd have to do is factor the denominator. So assuming this is done or is not necessary, factor it fully. 3. Now what you're going to do is you're going to break up the fraction. Across each factor in the denominator. Obeying 2 rules. So A, the numerators must be generic polynomials 1 degree less than the denominator. Specifically 1 degree less. And 2, if there is a repeated factor. That is, when you factor the denominator, you get one factor with a power that's greater than 1, and some positive whole number greater than 1. You must also split this counting up to the highest power. I think that's kind of where we ended last time. So we did a few examples. So if you had something like some polynomial of a lower degree over something like x times x minus 1, you'd split that into x plus b over x minus 1. because the denominators have power 1, so you need the numerators to have power 0. If you have something like x times x squared plus 1, which can't be factored anymore over the real numbers, you would break that up into a over x plus the other factor is x squared plus 1. This is a quadratic, which means on top you need something 1 degree less, which means you need a linear function. So something like x plus c. Accounted for all possible coefficients going down to the 0 coefficient. And if you have something like, let's say you had x squared times x squared plus 1 squared, but let's make that cubed just for emphasis here. Then there are really two factors here, x and x squared plus 1, but they're repeating. The x is repeated 3 times. So what you're going to do is you're going to count up with the factors. So there's an x squared, and x cubed. And again, you're paying attention to the factor on the inside, so we're thinking of x here. So that's a first degree polynomial. So the top must be a 0th degree in all cases because you're really focusing on the x here. The x is the factor that's repeated. So we're focusing on the x specifically. Here it's just repeated twice. Here the x is repeated 3 times. So the top must go with the power of the inside factor. You count up to it. I briefly showed why this was true last time, but you do the same thing here. So for the x squared plus 1, you start at the first power, but then of course you have to count up to the second power. And on top of those, you'll have polynomials that are 1 degree less, which makes them linear. So something like dx plus e, fx plus g. And that would be how you break up fractions like that. And of course, in the denominators, if you're looking at the general form, the denominator here, if I were to multiply out, I would get a 2nd degree polynomial, which means my p of x must be at most a 1st degree. If it's a 2nd degree or higher, I'd have to actually manipulate it or do long division before even thinking about this. Similar here, if I multiply this out, I would get a 3rd degree polynomial in the denominator, which means the p of x on top should be at most power degree 2. If it's not, I have to use long division or something to simplify it before even doing this, and that should be. And I think that's where we kind of ended last time. Now, we are down to, how do you actually go about finding what numbers makes this work out? Now those guys here, these are usually called the kind of like the constant of integration, they're just called the arbitrary constants. And so the question is, how do we find them? Well, there are 2 main methods, and sometimes I like to mix and match. So let's look at a couple of them. Now, this is the one I kind of like more, and if it works, it's kind of going to be the one that I'm going to try to get to work, because it gives me some nice numbers right away. So if you have, so step 1 in this is to multiply both sides by the denominator on the left. And then what you're going to do is to choose convenient constants for the Now, convenient here has I'm using this in a very specific way. Basically, convenient means for us, it will wipe out all arbitrary constants except one that you can solve for. Repeat this process until you find all of them. Okay, so let's actually see what that would look like. We'll do many more examples here, but give you a couple quick examples off the nose. Let's say I had something like 1 over x times x minus 1. I want to break this into partial fractions, the sum of two fractions that will add up to this one, and they themselves are fully reduced. So the first step, by going through the first three steps, I would break this up into something over x and something over x minus 1. These are both first degree polynomials, so there should be 0 degree polynomials on top. So that would be the first step. Now, what I would do, and this is where I'm applying method 1 as quoted here, is I'm going to multiply both sides of this equation by the denominator on the left. So I'm going to take this whole thing, I'm going to multiply by x times x minus 1. This would result in 1 equals a times x minus 1 plus b times x. Do we see how that happens? So if I multiply this by that, the x's would cancel, I would get this. If I multiply this by that, the x minus 1s would cancel, and I'd be left with the x. So I get this new equation that has no fractions in it. Now, what I want to do is pick some convenient numbers that's going to allow me to solve for the a and the b one at a time. Any convenient numbers that you notice? Yeah?
0 and 1.
0 and 1, pretty convenient. Now, this means that if I set x equals 0, what this implies is that I would get 1 equals a times 0 minus 1 plus b times 0. This wipes out the b from the equation. I would then get 1 equals minus a, or in other words, my a is equal to minus 1. I can then repeat this process by choosing another convenient number. Let's say x equals 1. Because this equation must always be true for every x, it will in particular be true at 1, so that would look like a times 1 minus 1 plus b times 1. And so that, of course, is a times 0, so that goes off to 0. And then I end up with b equals 1. And therefore, I can say one over x times x minus 1 is actually minus 1 over x plus 1 over x minus 1. Or you can write the other way around if you don't like the minus being in front. And you can check this. You can add those two together and you would actually get that as the answer. Right? Create a common denominator, add them together, do the cross multiplication thing, add them together, you're going to get that. So these are the partial fractions. Any questions on this process? Now, sometimes there are no convenient numbers in the above sense. you'd still be able to set up equations by a similar process. To solve for constants. Let me show you an example of that. So, yeah, every now and then you're super lucky. You can pick numbers where literally every arbitrary constant gets wiped out except one, and you just solve for that one. Sometimes though you can't really do that. So let's kind of modify this a little bit. So let's say I had something like this. Now, of course, going through the first three steps, this is going to break up into, maybe someone should tell me what these break up into.
A over x plus bx plus c over x squared plus 1.
Then, following this method, multiply both sides by the denominator on the left. What am I going to end up with here? 1 equals?
A times x squared plus 1 plus bx plus c times x.
All of that times x, so in parentheses. Or in other words, maybe now, right off the bat, we do have a convenient number. If I set x equal to 0, what's going to happen is I would have 1 equals a 0 plus 1 plus b times 0 squared plus c times 0. Those guys both go away. A is the only one left to solve for, and I can get a right here. However, you would notice that there is no such number that will work for the b and the c, right? There's nothing that I can plug into that will kill the a and the c and leave the b unchanged. In fact, there's nothing that I can plug into to actually kill the a term, because x squared plus 1 is never actually 0. So you don't really have any convenient numbers in the traditional sense. And by the traditional sense, I mean the thing I told you about 2 minutes ago. It's been a tradition for 2 minutes. But what you can do is you can just keep plugging in numbers. You can't get the perfect numbers. Just plug in any other random ones. Maybe something small, like 1. Okay? And what you're going to have happen is something like 1 equals 2a plus b plus c. Now there are all 3 variables there, but at the moment I'm not too worried, because for 1, I know what a is. So I would essentially get minus 1 equals b plus c. Then I can plug in some other random number. Let's say x equals minus 1. And doing that, I would get 1 equals 2a plus b minus c. But again, I know what the a is. So I can get, if I plug in the minus 1 here, where am I? If I plug in the 1 here for a, I get minus 1 equals b minus. Now, again, I didn't get convenient numbers in the nice sense that I can kill all the arbitrary constants except 1, but by plugging in a bunch of numbers, I did get a system of equations here, which I could actually solve. So, for example, if I add these two equations, I would get minus 2 equals 2b. This means that b is equal to minus 1. And as a consequence, if I plug in b equals minus 1 into either of these equations, I would immediately get that c is 0. So again, not super convenient, but it didn't cause too much trouble by plugging in some other small numbers here. So ultimately now, I realize that 1 over x times x squared plus 1 is equal to the a over x plus the bx plus c. So this is minus 1x plus 0 all over x squared plus 1. Or in other words, this is 1 over x minus x over x squared plus 1. And once again, you can actually check that these two will add up to that. You can also appreciate that if I were to ask you to integrate this thing over here, based on what we have so far, that will be problematic. Not that it's impossible, but probably the best method that we had before partial fractions to deal with something like that would be trig substitution, where I just see the x squared plus 1 term and setting x equals tan theta can help me get rid of that guy. However, by realizing that this is that, this thing can be integrated pretty easily. That's just your ln of absolute value of x, and here I would do a substitution, u equals x squared plus 1. And that will give me the 1/2 of ln of x squared plus 1. So that's method 1, generally speaking. Just plug in a bunch of constants. Worst case scenario, you're going to get a system of equations where you have to solve for the variables later than that. Best case scenario, you'll be able to pick numbers that kill all the arbitrary constants except one that you really want to solve for the time. Questions on that? Here's another way to go about it. And of course, these methods are just informed by algebra. If you have an equation like this, you can multiply both sides by a non-zero number. It's not going to change anything. So, if we look at method 2, this one is to basically, it starts out the same way. 1, multiply both sides by the denominator on the left. It gets different in step 2 though. In step 2, what you're going to do is you're going to multiply out the right side, combine like terms, and equate coefficients of like powers of x. 3, you'll obtain a system where you can solve with arbitrary constants. Let's see what this method would look like. And like I said, sometimes you mix and match. Sometimes depending on the mood, one might be more annoying to do than the other one. Maybe I'll try it with this same one. Maybe I'll give you a slightly more complicated one later on. But again, let's start with this one. We know that this will break up into ax plus bx plus c over x squared plus 1. This means that 1 is equal to a times x squared plus 1 plus bx plus c times x. Now at this point what I'm going to do is I'm going to multiply out the right side. And I'm going to combine like terms. So x squares, I'm going to combine them. Notice I have a plus b x squared. That takes care of these two terms here. And there is a term for the x. that is the C, which is phi is lonesome. And there's a constant term, the coefficient of x is 0, which is the A. Now we manipulate this to look like the to equate coefficients. Now, sometimes you might have to fill in some guys to make this obvious. So you can look here where we have this situation going on. Over here we have a 1, but you can be a little bit creative and realize, well, there you can imagine that we would actually have a 0x squared plus a 0 times x plus a 1, right? Now, if you think of it that way, certain things can happen. We can start to equate coefficients. So obviously the 1 is going to be equated to the A. Then of course, the coefficient of x on this side must be equal to the coefficient of x on that side because it's an equation. We have to have the same number of x's on both sides. Similarly speaking, we have to have the same number of x squares on both sides. Right? So we match up the like powers of x, multiply out, combine all the like terms, then match up the terms on both sides. We have to have the same number of each power of x on both sides because it's an equation. And so what that ends up giving you is a system of equations so by equating the black, we get A plus B equals 0. By equating the green line, we get C equals 0. And by equating the blue line, we get 1 equals A. Now, the systems of equations aren't always that easy. This was just a simple example to illustrate the idea here. Right here, you can immediately find A and C. And of course, you can just go and plug that A in equals 1 here. And solve for the B. So you can get all three that way. And then you can go back and you can plug it in. A, which is 1 over x. The B is minus 1x, and the C is 0. And in some context, dealing with this side is going to be easier than dealing with that side, in particular in a calculus context. Questions? We're all clear on this one? Okay. Let's do some examples. Maybe I'll give you guys a few minutes for this one, and we'll do problem 2 together. Find the partial fraction. The following. A. Now this is one that we've seen before. This was the motivating example to this section where I just told you the answer, but here you get to find the answer for yourself. So hopefully by the time you get through all of those, you'll get the idea. So I'll give you a few minutes to work on these. And then we'll probably go through those together. We'll have just a slight intermission. So people aren't just watching nothing happen for like 10 minutes. So I will stop.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. The show will start in 4 minutes. will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
And we're back. Intermission over. Let's see where we got. Let's go through the first one. Shouldn't be too bad. I will make a slight detour while I'm going over it though to show you something pretty cool. But let's actually go through the first one. 1A. Okay, what was the first step here?
Factor the denominator.
So first, you would check that the top is of a lesser degree than the denominator. The top is a 0 degree polynomial, the bottom is a 2nd degree polynomial, so that actually works out. So the next step is to factor the denominator. So to multiply and get 6, maybe a 3 and a 2 would work, and if I subtract both of them, I would get a -5 middle term. So I kind of know that this is going to end up being that situation. So in other words, we get that 1 over the x minus 3 times x minus 2 is going to give us that. What I can do is I can multiply both sides by this denominator, and I would get a times x minus 2 plus b times x minus 3. And pretty nice to use method 1 here, so that's what I'm going to do. So x equals 2, I would get 1 equals, well, b times 2 minus 3. In other words, that's minus 1b, so b equals minus 1. If x equals 3, plugging that in, I would get 1 equals a times 3 minus 2, and the b would go away. So that means that a equals 1. And so it turns out the answer to this one is, this can be broken up into 1 over x minus 3 minus 1 over x minus 2. Now I kind of knew that was the answer because I actually did this example before, but how many people actually got that answer? Okay, good. Now, here's something cool. Can't get too excited. 200. It's like, here's something cool. I started getting excited, now I'm coughing. Oh god. Okay. Now, there's a theorem called the Residue Theorem. In a course called Complex Analysis. So at that point, you need to have some multi-level calculus under your belt to actually take this class. So after Calc 3, it'll be a nice class to take if you're a math major. You're going to learn a lot of stuff in that class, including all new methods on how to find integrals. That's going to seem like magic. Now there is one particular theorem called the Residue Theorem that helps us find integrals for complex valued functions. I can't really state the theorem because it's not going to make sense if I state it. It talks about poles and holomorphic functions and all that kind of stuff. But there is one specific application of this. When we have non-repeating linear factors. If you have repeating linear factors or you have non-linear factors, like an x squared plus something, then applying this theorem gets a lot more complicated. It involves limits and taking derivatives and factorials and all that sort of stuff. But at the linear case, you end up taking, if you plug it into the formula, you end up taking the factorial of 0, the 0th derivative, which means you don't actually take any derivatives, and the limit part just becomes really nice and easy. Here's how it actually applies, like it would apply to this one. So I'm not going to tell you the theorem, I'm literally going to tell you a trick that will work with the linear case. So if you look like this guy again, you know that this is a over x minus 3 plus b over x minus 2. And I know that this becomes x minus 3 times x minus 2. So 1. Now, here's the cool trick. If you want to figure out what the a is, there's actually a shortcut for it because it's a non-repeated linear factor. It looks like a line to the power 1. Same thing here, it looks like a line to the power 1. That's the only thing that occurs here. Here's a trick that you can do, is figure out what makes this 0. For a linear factor, it'll be easy. Of course, in this case, x equals 3 will make this thing 0. Then what you're going to do is you're going to go to the original. Ignore. It takes a while for me to write it out, but once you actually know the method, it's going to be super quick and super easy. Ignore the x minus 3 factor and plug in x equals 3. You'll actually get, this will give you a. Right now, let's actually see what that would actually look like here. So I am going to go So for A, essentially go back to the original, x minus 3, x minus 2, ignore this. Sometimes people call it the cover-up method because they just cover it with their hand, and plug in, evaluate that at 3. You will get 1 over 3 minus 2, which ends up being 1, and that's your A. That's actually A. And if you go for B, do the same thing. 1 over x minus 3 times x minus 2. Figure out what makes this guy 0, which is x equals 2. Then you kind of cover it up, you ignore it, and you plug in, evaluate the result at 2. You will get 1 over 2 minus 3, which is minus 1, and that was our B. That will literally always work. It's crazy, but it works. It works with linear factors. You'll see something like this. Let's say I have, I don't know, 5 over x minus 5 times x plus 3. I know that this is going to break up into x minus 5 and x plus 3. X equals 5 makes that 0, so I go over here, cover that up, plug in 5. I get 5 over 8. That's going to be what goes on top. X equals minus 3 makes that 0, go over here, cover that up, plug in minus 3, get minus 5 over 8. Turns out that's the answer. So it's really cool, right? So there are times when if you see me or any other professor does partial fractions like superhumanly fast, chances are in his head he's thinking of the residue theorem. So it's one specific application that you can apply really easy, but the caveat is in this form it only applies to linear non-repeating factors. Like if here now you had an x squared plus 1 times x plus 3, it doesn't work anymore. This one is going to involve you taking the first derivative and a limit if you apply the formula. So it won't work with that. It's not going to work if you have like a linear factor to a power. So that also requires some finagling, but as long as your linear factors aren't repeated, this cover-up method will actually work. Figure out what makes this guy 0, cover that up, plug in that number, that'll give you the numerator of this guy. And the top doesn't have to be a constant for this to work. You can do this for lots of stuff. So I can say, okay, I have x squared plus 1 over, let's say, x times x minus 1 times x plus 2, whatever. So I know this is going to split into something over x minus 1, and something over x plus 2. What would those numbers be? Well, 0 makes this denominator 0, so we're going to cover that up and plug in 0. I would get 1 over minus 1 times 2. That's the answer. X equals 1 makes this 0, cover that up and plug in x equals 1. I would get 2 over 3. That would be the top of that one. X equals minus 2 makes this 0, cover that up and plug in minus 2. That will give me 5 over minus 2 times minus 3. So this will actually be minus 1 over 2x plus 2 over 3x minus 1 plus 5 over 6x plus 2. And you can check that that's actually the partial fractions. You add those together, you'll get the original. So it's a neat little trick. Not really a Calc 2 thing, but one specific application of this big theorem applies very nice to the partial fraction scenario when you have linear factors. So I thought that was pretty cool. You might think it's cool, so I decided to show it. Okay, but that's a thing. So you can skip both method 1 and method 2 that I told you and use the cover-up method in this specific scenario. Because the other scenarios, the formula gets more complicated for the other scenarios. And at this point, it's just kind of not worth it at that point to actually go through it. Yeah, so that's that. You might even find cause to use that later on. But let's go on to B. How many people actually got through B? first step here?
Factor the denominator.
Factor the denominator. So we notice that the highest power on top is a 2, the highest power on the bottom is a 3, so it's a proper fraction. So the first thing I'm going to do is factor the denominator. Let's go to x times x squared plus 2x plus 1, and that factors again. So you have to factor the denominator fully, just keep factoring. Well, that's just x plus 1 all squared. So of course that would be a over x plus b over x plus 1 plus c over x plus 1 squared. And what do we do now?
Multiply by the denominator and the left.
Multiply by this, so we get. So multiplying by this, the x's would cancel, you get a times x plus 1 squared plus bx times x plus 1 plus cx. At this point there are some convenient numbers that can work out for us, so I would plug in say x equals 0. On this side I'll get 6, on that side I would get a, those two get wiped out, so a equals 6. X equals minus 1, also pretty convenient. So I plug in minus 1. On this side I would get 5 minus 20 plus 6. On that side I would get, that would be 0, that would be 0, and then I would have minus c. So this is plus 11 minus 9, so that's minus 9 equals minus c, or your c equals 9. And then the only thing that's left now is the b. And there's no convenient number that we can think of that will kill the a and the c and leave the b. So at this point, I probably just plug in a random number, sticking with method 1, because I'm already in that mode. So I probably plug in, say, x equals 1, right? It could work in theory for any number, so I could plug in x equals 517, but why would I do that? 1 is a very nice number, the smallest number I can pick that I haven't picked before, so smallest whole number. So let's actually do that. Plugging in 1, I would get 5 plus 20 plus 6 equals, that would be 4a plus 2b plus c. And the good thing is I actually know what a is already, and I know what c is already. So that means over here I would have 31 equals a was 6, so that's 24, and c was 9. So 24 plus 9, that's 33, subtract 33, I get minus 2. So your b equals minus 1, and therefore is equal to a over x plus b over x plus 1 plus c over x plus 1 squared. How many got that? If anyone didn't get that or didn't get this far, any questions? And again, look at that, that looks horrible, that's so complicated, man. Integrate that, oh come on, give me a break, Jhevon. Yeah, but you do this now, it's like, you can do each of these in your head, right? It's that, becomes that simple. Let's do this one. Did anyone get through C? Numbers are getting smaller now, let's see. In the case of C, we had 2x cubed minus 4x minus 8 over x squared minus x. X squared plus 4. So what do we do here? factor the denominator. No. In the beginning, it might seem to you like it's fully factored, but it's not. There's a common term of x here. That's why when I say factor the denominator, I put fully and put an exclamation sign, because if it can be factored further, you definitely want to do it. So this is going to go to a over x plus b over x minus 1 plus cx plus d over x squared plus 4. The x squared plus 4 can't really factor over the real numbers very nicely. So again, I'm going to multiply both sides by the largest denominator over here. That's going to give us 2x cubed minus 4x minus 8. By the way, the denominator was a 4th degree, the top is a 3rd degree, so I know this even makes sense to start in the first place. So I would have a times x minus 1, x squared plus 4, plus b x times x squared plus 4, plus cx plus d times x minus 1. That's about right. Okay, so now we have 4 constants to find. So let's actually get started here. X equals 1 seems like a nice place to start. That'll make this 0, that'll make everyone here 0. So I would simply have phi b, right, from the x equals 1 over here. So that's minus 12 plus 2 makes this minus 10. This means your b equals minus 2. What else can we do? X equals 0. Someone suggested, also seems convenient. So I'll plug in x equals 0. See what we get here. We would get minus 8 on one side, and this will go to 0, that'll go to 0, and I'll just have minus 4a. So this means that your a is positive 2. So there's nothing else really convenient at this point. I mean, we could keep this up, start plugging in random numbers. We could also just expand everything and actually combine like terms. But yeah, with the way this looks, I probably wouldn't want to do that, even though it's a given method. But that's just a personal thing, that's just me. I'd rather just keep doing this drill than actually multiplying out these things. So that's what I do, I just plug in some other random number. So let's keep it small, let's say minus 1. And so what I would have is minus 2 plus 4 minus 8. And if I plug in minus 1 right there, I would have minus 10a. Because that would be minus 1 is minus 2. Minus 1 here would give me 5. That would give me minus 10. And here, plugging in minus 1, that's just minus 5b. Here, plugging in minus 1, I would have d minus c times minus 1 times minus 2. Let's clean this up a bit. And that's going to be minus 10 plus 4, that's minus 6. A is actually 2, so I'm going to plug it in, that's minus 20. B, do I know B? B is actually negative 2, so this is a plus 10. And this will actually give me plus 2d minus 2c. And so I get that this gives us minus 10, go over here, it becomes plus 10, so that becomes positive 4. I get 2d minus 2c, or I get that 2 is equal to d minus c, and I will file that away. Pretty much now I want one other equation with d and c as the unknowns, and then I can actually pair it with that and figure it out. So I would pick another number. We already picked 1, 0, minus 1, maybe going up to 2 would work. So x equals 2. 2 here, that's 8. 8 times 2 is 16. 2 here, it's minus 8. Minus 8. Right, so on this side it's 0. Then if I'm plugging in 2, this becomes a 1. This will become an 8, so that's 8a. Plug in 2 here. This will become an 8, that'll become a 2, so that's 16b. Plug in 2 here. This will become 2c plus d. Two here, you get a 1, 2 here, you get a 2, so that's all just times 2. Now a is 2, so here this will be 16, plus b is minus 2, so this will become minus 32, and then I would have plus 4c plus 2d. That will become minus 16. Move it over here, I get a positive 16. Divided by 2, I get 8. Equals this. I have those. So I'll call this equation 1, call this equation 2. If I take, say, 2 minus 1, that's going to give me 8 minus 2, which is 6. D minus D, that's gone. 2c minus c, that's 3c. So our c equals 2. And now I can just plug in c equals 2 here. This would mean that 2 equals d minus 2. This means that your d equals 4. So finally, we get to this was a over x plus b over x minus 1 plus cx plus d over x squared plus 4. That is going to be equal to, b was minus 2, if I recall correctly. The a is positive 2. The c is 2. The d is 4. So that would be the answer. Did you get that one? So you can see the arithmetic is going to be annoying a little bit depending on the problem, but it's something that you can figure out. And it just might be worth it if what you really want to do is integrate something like that. Integrating these is going to be a lot nicer. Stop there. I'll see you on Thursday. We'll finish up the rest of it. Or you can be sure to try and work on this for tomorrow. So tomorrow is a quiz week. So the quiz technically is everything up to last week. So technically you don't need to know this for the quiz, but I might throw in a bonus problem on this as well as the next section. So what you do need to know up to the quiz is everything we did last week, including how to actually break up a partial fraction. So you don't need to know how to find the A, B, C, D technically for tomorrow's quiz, but you should need to know, at least know how it would look if you broke it up to do that.
Thank you.
See you tomorrow. Take care.